All right. The new pivot row. This was the second basic feasible solution we found in the dictionary form, with x1, x4 becoming 0, and the solution telling you what the constants, the constants on the right side tell you what the values of the basic variables are. The equation version of this is simply z minus 5 halves x1 plus 3 over 2 x4 equals 12. This equation. Then we have 3 over 2 x1 minus 1/2 x4 plus x3 equals 2. The last one, x2 minus 1/2 x1 plus 1/2 x4 is equal to 4. The same equations written in the usual form with all the variables on the left. And the tableau, after the pivoting operations, simply gives you the coefficients you would see here. So I'm not going to go through the pivoting operations, but if you just follow the pivoting operations, you should get exactly the coefficients we see in the equation form. The basic variables will be z, x3, and x2. That's the x1 column. The x2 column is a unit vector. Of course, for basic variables, you always have your unit vectors. For x3 column, we have 0, 1, 0. And for the last one, we have 3 over 2 minus 1/2. Yes, if you close that door, we don't have enough air circulating. That's the problem. Maybe we should open another window then. Yes. Because otherwise, you know, it's getting too warm here. At least for some of us. Not for you, but for me, it is getting warm. What is this? 1/2 And then you have 12, 2, and 4. All right, you should work on the pivoting operations because normally you're not going to have the information for the dictionary form and the equation form in carrying out these operations. You only work from one tableau to the next one. And the only transition is via pivoting operations, or, of course, you can also use simply elementary row operations to create your unit vectors in the basic columns. Okay? These are the basic variables here right now. Okay. I again inspect the coefficients in row 0, and I'm trying to increase my objective function value, so I choose, there's only one negative here, I choose this one as my entering variable. And then you look at your ratios, but the ratios you look at in this case will be, there's only one ratio. So this particular variable, x3, is the exiting variable. The other one has a negative number, and that negative number tells you that x2 will be increasing as you start increasing x1. Okay? The same reasoning. That, you know, the reasoning, it's all the same. It's just the way you handle things become a little bit different. Okay, so you pivot on that. And then when you pivot, why don't you go ahead and do your pivoting operation and see what you get. Divide the entire pivot row by 3/2. So when you do that, you get 0 here, 1 here, 0, 2/3, minus 1/2 divided by 3/2. That's too complicated for you. How much? Minus 1/3. And the right side? 4/3. Okay, that's the new pivot row. So you add... All right, where am I? Okay, I'm trying to create a 0 in place of minus 5/2 here, which means that I add 5/2 times this pivot row to the original top row, okay? So that will give you 1 here, 0 here, the rest you ought to calculate. This one will not change, 0. This will be 5/2. I don't know what that will be. You do it. I'm not very good with computations. 5/3? Okay. I believe you, Sibel. You took it from there, huh? Of course, you can copy it down from the dictionary form, which we already have. Yeah. What is the last row? Somebody? I know you have a 0 here, you have a 0 here, you have a 1 here. I'm lazy. Let me just copy it down. 1/3 and 1/3 again. And 14/3. That's what you should have. Which, of course, corresponds to the dictionary form. And for the equation form, you can fill it in. You just take the tableau and write it in equation form. That's it. Okay? Okay, at this point, I'm looking for a negative number in row 0. I don't find any. And so this is optimal because all the adjacent basic feasible solutions are inferior in objective value. Okay? That's how you carry these things out numerically. Now it's time to look at this in terms of bases and so forth to gain additional understanding. Okay? So let's just have a clearer understanding of what's really going on with the simplex method. Numerically, it's really simple. I'm going to consider the standard form problem. Expressed in this way with rank of A equal to M. There are M constraints here. So A is M by N. And you've got N variables. So A is an M by N matrix. Okay? So I'm going to assume that we have a basis B consisting of some M linearly independent columns of A. There is a theorem which told you that taking N active constraints that are linearly independent will tell you that N minus M of them will have to come from the non-negativity part because M of them come from here. The remaining N minus M will come from the non-negativity part. Those variables, when taken as equal to 0 or as active, in order for the linearly independent constraints, active constraints to be linearly independent, the corresponding columns corresponding to the remaining variables should be linearly independent. There is a theorem on that. Okay? That's why we have this basis. So we partition the problem in the form minimize C sub B xB plus C sub n xn subject to bxb plus nxn equals b, xb, xn greater than or equal to 0. So what we did is we partitioned A in the form B and N, where the basic columns are put on the left front portion of A matrix with column reindexing as necessary. And of course, X is partitioned in the form XB, XN, where XN is the non-basic part. And what else? C is partitioned in a similar way. CB, CN, basic costs, non-basic costs, so on and so forth. What else? That's it. And so with the partitioned form, this problem is nothing but the old problem in written out in the form of a or relative to the basis B. Okay. And the value of the objective function, we term it by the variable z, which is your additional variable. And the row 0 form of the problem is simply the same thing. You try to minimize z subject to row 0 refers to the definition of z. This is your row 0. The remaining part is already in the constraints. So row 0 refers to this upper portion of the boxed set of equations, and rows 1 through m refer to the remaining part, the lower part. Okay? That's what we did in the example problem also. I'm just trying to match what we're doing here with the example. All right. Now, in the example, we saw for basic variables a lot of unit vectors, whereas here we don't have any unit vectors. Okay? So let's just number these. Pre-multiply rows 1 through m by the inverse of the matrix, of the basis matrix. When you do that, we're talking about pre-multiplication here, rows 1 through m. What you get is, you get B inverse times B, which outputs identity, so that part gives you XB. And then you have B inverse N here. And on the right side, you have B inverse B. That's what you get. And the non-negativity, I'm just keeping track of that on the side, so we're not doing anything with that. Okay? So this tells you what the solution should be. With xn, the non-basic part, set equal to 0, this gives the current basic feasible solution corresponding to or defined by B. Defined by the basis B. What is it? It is xb equals B inverse B. And xn equals 0. And what is the objective function value? Well, xn is 0, so it will be cb times B inverse B. That's a number. Even though it looks very complicated here, it's just a number. Okay? All right, that's your current basic feasible solution. Your book gives a name to B inverse B. It's just a column vector. It just calls it a modified version of the original right-hand side, so B bar rather than B. Okay? Xn is 0, and this one, we call it, well, it's CB B bar. Okay? And because this is a particular solution, let's put the bars on top of them. It's a basic feasible solution. It's a particular solution. corresponding tableau basic variables are listed here. Z is the basic variable associated with row 0. So when you pre-multiply, this is what you get. And that tells you what the equations look like here. Z does not show up here, so you have a big vector of zeros here for Z. XB has the identity as the matrix of coefficients. That's I times XB. Xn has B inverse n. So that's a matrix. Those are the numbers that show up underneath your non-basic variables. The right side is your B bar, the current solution. The row 0 information is not available yet. So I'm not going to fill it in. Okay? For any choice of xn, not xn equal to 0, but for any choice of xn. So I can take xn to be anything. As long as it's non-negative, I should be able to do it. Okay? The solution for xb is, what is it? xb is equal to B bar, which is B inverse B, minus B inverse n times xn. So, as long as I fix xn, I am always able to choose xb according to this equation, so that all my equality constraints are satisfied. As long as you do it this way, your equalities will be satisfied. What is it that may be violated? It's the non-negativity that may get violated. Even if you choose xn non-negative, xb may turn out to be negative in some components depending on what particular xn you happen to choose. Okay? So, nevertheless, this is the equation that relates the xn's to the, or the non-basic variables to the basic variables. Substitute this in the equation z equals cb xb plus cn xn. And then you get the following. Z is equal to, in that case, cb times xb plus cn times what you see here, B bar. No, sorry. I'm doing it in the incorrect way. CB times what you see here for XB, which is B bar minus B inverse n xn, right? Plus Cn xn. So for XB, I simply substituted what I see here, okay? Which, upon simplification, will give you CBB bar plus something times xn. All right, so let me take this as plus. What do we have? Cn minus CB B inverse n. Okay, that's what you would get. I'm going to give a name to this. This is just a vector. It's a row vector. that has as many coordinates or components as xn does. Okay? So let's give a name Rn to it. Actually, let's call it minus Rn rather than plus Rn because, well, there's a reason for that. So let's define Rn to be the negative of what you see in the parentheses. Okay? With that, row 0 reads now z minus what you have there. So z plus Rn times xn equal to b bar. Cb times b bar. Right? Okay. So going back to my tableau here, z has a 1 here from row 0 equation. And then xb's don't show up in row 0. So you have a big row vector of zeros there. xn has Rn as its coefficient, vector of coefficients. So that's your Rn here. And what do you have here? You've got z bar, because that's your Cb b bar. Okay? That's my z bar here. So this part came only after I figured out what row 0 ought to be. All right, so we've got this for row 0. So if I partition the index set of the variables, 1 through n is the set of indices of the variables. I simply extract the basic indices, put them in one set, and put the remaining variables in another set. I sub n is the set of non-basic indices, and I sub b is the set of basic indices. So if you look at this equation, this simply tells you that z equals the current value z bar, that's your z bar, minus Rn xn. Rn xn is simply the dot product of a row vector with a column vector. So it's simply Rj times xj, where j refers to the non-basic set of indices. Okay? That's your dot product. So the rate of change in z, if you allow xj to vary from 0 upwards, is going to be the negative of Rj, okay? The coefficient for xj. If minus Rj, or if Rj is itself negative, then of course negative and negative will make positive, which means of course it's good to, what am I doing though? Did I write down a minimization or maximization? Minimization. So we're on a minimization problem. It's a minimization problem. So what you want here is what kind of a Rj do you want to improve the z value? If Rj is positive, This will be negative, which means you will be able to decrease the value of z from the current value. Okay, so if Rj is positive, then each unit increase in xj gives a reduction of Rj units in z. So any variable that has a positive Rj can be entered. Any non-basic variable xj for which Rj is positive can be entered, which means that it will become, or it can be made basic. Okay. We typically choose, we typically choose which one? The most positive one. Okay? And if you have ties for the most positive, of course you choose one of them, only one of them. For a maximization problem, the criterion to choose an entering variable is just the opposite. So as long as Rj is less than 0 for a maximization problem, that variable qualifies to enter. And typically, you choose the most negative one. Let me give a name to it. Let's call these Rj's reduced costs. Okay. So Rj is the reduced cost for the jth variable. And you choose the one with the most negative reduced cost for maximization problem. For a minimization problem, just the opposite. How do you remember these things? I never remember them. I simply... Believe me, I work out the entire thing and then I inspect my equation. And when you look at this equation here, it tells you when, well, z bar is the current value of z. Xj can only be made positive. So if I'm minimizing, I want a minus Rj to be negative here, which means Rj should be positive. You know, you just reason it out, okay? As long as you can somehow get there. If you're not able to get there, God help you. I don't. Just in that case, maybe memorize, okay? All right. This also tells you what the stopping criterion is. The current basic feasible solution defined by B is optimal if Rj are all less than or equal to 0 for a minimization problem. and if Rj are greater than or equal to 0 for every j for a maximization problem. Okay? All right. So let's decide on the exiting variable now. So at least you know what to do or how to choose your, how to select your entering variable. For a minimization problem, you just choose one that has the proper sign for the reduced cost. Okay? So it's positive for a minimization problem. Suppose we decided to enter a variable xp as Rp is positive. The initial problem I stated is a minimization problem, so I'm positioning myself relative to the minimization problem. Okay? So with xp allowed to become positive while all other non-basic variables still being kept as non-basic. We have the following situation. What was xp? Xp was equal to the current vector b bar minus b inverse n times xn. That was the equation for xp. Now this part is all, well, all xj's are 0 here except for one of them. Okay? So this is 0 except the variable xp. Okay? So this will simply tell you b bar is xp is equal to b bar minus the column ap associated with the entering variable xp, except that you also have a b inverse here. Let me just write this in cleaner form. So this tells you xp is equal to b bar minus b inverse times the column for AP xp. All the other ones, they drop out because they are already, or they will be kept 0. If you did not follow what's going on here, ask me now. Some of you looked puzzled. I can detect that. There's nothing mysterious here. If you look at this, that's b inverse times n xn, which is the same thing as b inverse times column, the columns, you know, whatever they are, let's call them aj1 up to ajk. These are the non-basic columns times xj1 up to xjk. K equals n minus m here, okay? So b inverse aj1 times xj1 plus aj2 times xj2, so on and so on. It's just a summation, if you think of it that way. And in that summation, all the terms drop out except the one corresponding to p. Okay? So that's why I've got that. All right. So this tells you how to express xp as a function of xp, the incoming variable. We want xp to be non-negative, which of course tells you that b bar minus b inverse ap must be times xp must be non-negative. This is a vector inequality. We're talking about a vector here, you know, m vector. So if you look at each vector, each coordinate of this vector in decomposed form, this simply tells you that the ith value inside b bar minus the ith value here, which I'm going to call yip times xp, that should be greater than or equal to 0 for each of the i's going from 1 up to m, where y is the vector, or y sub p is the vector defined by b inverse ap. So we just gave a name to it. Okay? Yp is a column vector. B inverse ap is the definition of yp. It has m components in it. The ith one is yip. Let me come here. P, and it has components y1p, the ith one is yip, the last one is ymp. Okay? I had too little space there, so I wasn't able to write down what I am trying to express to you. With this, the equation xb equals b bar b inverse ap times xp non-negative. This part is simply b bar minus yp xp greater than or equal to 0. Okay? And if you write this in equation form, of course, you have the following. b1 bar, bi bar, bm bar minus y1 p, yip, ymp times xp greater than or equal to 0. That's the inequality system we're talking about when you impose non-negativity on xp. So this is simply the first basic variable, which I'm going to call xp1. The ith one, xp sub I, the last one. Okay? So, these basic variables are supposed to be greater than or equal to 0. And of course, when you look at this, this simply tells you the ith one is this one. Now, xp will be allowed to become positive. If xp is positive, if yip is 0, we're looking at a particular I here. If yip is 0, then 0 times xp will not change that. So if yip equals 0, then the basic variable xpi, the ith one, will simply be the old value. Okay, no change. If yip happens to be less than 0 or negative, then xpi will change in what way? It will be the old value minus a negative number yip times xp. This will always stay greater than or equal to the current value, which we know is greater than or equal to 0. Okay? Why? Because yip is negative, negative and negative makes positive, so xp is also positive. So you're adding something to the current value. If yip is positive, on the other hand, xpi becomes the old value minus some positive number times xp. In that case, of course, you need to impose this. For the other ones, no need to impose. No need to check, because they won't make your xpi negative. Okay? This one, you have to pay attention to that. And of course, whenever you impose this, xp is less than or equal to bi bar divided by the positive number yip. That's what you've got. Okay? Blocking occurs with the minimum ratio, if you refer to this as your ratio. Okay? It's the ratio of the current value divided by whatever coefficient you've got for the entering variable in that ith equation. So, the exiting criterion is defined by identifying the minimum, identifying a particular ratio, BR divided by YRP, where this one is the minimum of the ratios, BI over YIP. The minimum taken over those I for which YIP is positive. Okay? So for the positive ones, you look at the ratios. Of the ratios, you choose the minimum. And a minimizing will be defined by some index R. If you have more than one such indices, fine. Just pick one. Okay? And so the rth variable, xb sub r, the rth one, not xr, but xb sub r, exits. Because that's the one that blocks. So, xp enters, xp sub r exits, and you get the new solution, but we're just about out of time right now, so I'm going to stop here. And next time we will see how to make some sense of this using the tableaus and etc. I know it's too much information for one day, but nevertheless, you survived. I guess you can survive the next one as well. Okay.